I work in computer vision domain, and today I will be discussing generative AI and its applications in computer vision in images and video domain. I will be, as you all know, ChatGPT is one of the very famous applications right now, use cases of generative AI. In vision domains, tools like DALL-E, Midjourney, which can generate images as you want based on your text or based off your input image. I will be showing you those use cases as well, but this generative AI talk will be oriented to computer vision, not related to the text, the ChatGPT, all those applications. We'll be covering, I have already delivered a data hour on computer vision where I covered few computer vision models. I assume you to have knowledge about what are classifiers, what are, segmentation networks. If you don't have, you can go through that data hour. I will share the link after. I gave it here, I think 2 months back. So we'll be covering shortly the recap as well. So continuing from there, I assuming some PyTorch knowledge that I covered there, but need not to worry. I will try to give you a quick recap. Based on that, I will be covering some prerequisite models. Those are very famous in generative AI domain, GANs and variational autoencoders. Based on that knowledge, I will be showing you how algorithms like stable diffusion, which is a backbone of all latest generative AI models in computer vision. You can, if some of you might know about DALL-E, which is also from OpenAI, which is capable of generating all kind of images. We'll be discussing some challenges that people are facing in generative AI. We'll be saying my opinion on future of generative AI and concluding the slide. All of this is based on our experience that we are using in industry for generating data because, yeah, these data is also very important for training deep learning models. So for quick motivation, few days back, there's a very famous professor from IIT Bombay, Amit Sethi. This is from his slides. He showed that he was delivering a talk to leaders in AI. He showed that that people were thinking that AI is declining or saturating, like with convolutional neural networks, they were gaining very high popularity. But now generative AI is the next boom that AI is seeing. And yeah, so AI is a branch which will have many peaks. It will expected to uh, expected to have many peak, unlike other technologies which is get saturated over time. Yeah. Yeah. So as I said in previous talk, I discussed about some classifier, let's say classifying images to cats and dogs, regression networks, ranking, matching, or yeah, such techniques. So these all comes under the predictive AI domain. But we are today talking about the generative part. It will give us generate the text as we want. For example, you can ask ChatGPT to write a complete essay on, let's say, brushing on night versus brushing on day. It will generate all kind of data you want, text you want. DALL-E, as I again said, is a popular algorithm for images. MuseNet for music, and Gen 2 or Win in videos for generating videos. So this is the area, this is the difference between what I already covered, or you might popularly know, or what we will be discussing today. So we will be focusing on the generating part. Application, you already might know about ChatGPT. Like you tell it to ask it for burger recipe, it can generate data as you want. This is from DALL-E, one of the prompt I gave, and it can generate paintings and any kind of art. It can transform you into your animated version or put you inside, give you a funny haircut or all kind of applications. Yeah. So any doubts so far? Okay, not so far. Yeah. So we'll be giving, I have already covered GANs, but I want to cover them again. And yeah, some implementation of GANs in PyTorch. And we'll see how we can, because GANs are considered as a hello world program for generative AI. It has potential to generate uh, similar looking images that it has trained on new samples. So quickly, I'm giving a recall of all the things I covered in previous slides. In previous data hour, I went through some applications of computer vision, human detection, retail object detection, detecting sports players, which kind of insect disease it is. I covered what is a convolution neural network, what are its building blocks, how we can make using PyTorch. So if you even need quick introduction to PyTorch, I recommend you going through that data hour again. But today I'm mostly in, so yeah, these are few things I discussed there. Today I'm interested in generative AI. I'm interested in GANs. So GANs I already covered there, but I'm recapping, I'm iterating it again. So GANs basically is a game between generator and discriminator, where our main aim is to detect real looking images as it was in a training set. Yeah, so we it's a game between discriminator and generator. Generator is a person, is a network that take a noise and will produce images those look real as it is in training set, and discriminator's job is to tell that it is real or fake. So it's a game of balance between both of them. Yeah, so I discussed the loss function as well, discussed that yeah, how it's a min max game, that the same loss function is minimized by generator and maximized by discriminator. So far so good. I gave an example of a network like how we can use convolutional network neural network to generate images with a noise as an input. This is a generator architecture. Basically, I will be showing that in detail now in this. Yeah, pretty much it. So we discussed how we can we train GANs alternatively, once generator and once discriminator. Yeah, so yeah, is my screen visible, Vishal? I am now switched to the Colab, right?
It's visible. It's visible.
Yes, yes. So yeah, so DC GAN or convolution GAN, you can say, is very is straightforward, simplest GAN, which can be used to generate MNIST data. So for example, MNIST is a data set which has images like these, like numbers in it, very simple hello world data set in computer vision. So I covered this already, covering it again. Yeah, so basically, this is the architecture of generator. We discussed that generator and discriminator are two main networks in GANs. So this generator will just take a noise of 100, let's say 100 cross 100 numbers, and it will give us an image which look like MNIST. And in generating them, discriminator will help it. Discriminator will always tell it whether your generating image is real or not real. But discriminator is also getting samples from real data. Yeah. So yeah, so we'll be using PyTorch again to writing this network of generator. We'll be showing you how we can do that. OS and Torch library. Yeah, torch.nn is used for different layers in this network. We discussed that again, and for writing different loss functions in your torch, use torch.nn.function. Okay, so I will be training this for 20. I have trained it for 20 epochs. Batch size. This is the you don't give single image to the network, you give it batch wise to make the training fast. learning rate for your optimizer. I will show it, and we'll be using GPU for training it. So this is quickly about what MNIST is. Each image is 28 cross 28, and each has a label 0 to 9. Label, you can say, or yeah, each contain a number inside them. Labels are not so useful here for us. Yeah. So yeah, that is the one of the applications. So that GANs are so popular that you don't need supervised. You don't need to label your data every time in GANs. Yeah. You just need to know real or fake. Yeah. So using some another libraries from Torch Vision, these were from Torch. Torch Vision is also provided by PyTorch community, where Torch Vision contain multiple data sets and what operations we sometimes need to perform some pre-processing steps. So Torch Vision provide all those things. Also using Torch, some util operations for creating my data loaders. Yeah. So I'm loading data set from Torch Vision only. It has many given for practice, many data sets are given. I'm using MNIST as I showed you. Loading into data loader and just specifying that for train it's true, for test it's false. That's how I'm loading my data set. And also as I specify, I'm using a batch size of 128. Yeah, very simple. I explained it in detail earlier. You can visit that again. Yeah, so for GAN training, kernel size of 4 uh, is what I'm using. So this is how I wrote my generator part, as I showed earlier as well. If you want to write a network, it has to come inside a class in Python class in PyTorch. And this is a basic syntax. So you should have an init class where you define your network. For example, here in this image, you can see that you have 1, 2, 3, and 4 conveyors. So, sorry, deconveyors. So here I'm specifying 4 deconveyors. Yeah. So, yeah, 4 or 5, 5 deconveyors. Yeah. So earlier in previous slides, we were discussing about classifiers, where I explained what is a convolution layer. So basically in convolution layer, you take a kernel and slide it over each full image and learn some features out of it. So deconv is the opposite of that. Deconv is used to increase the resolution of the image. It's opposite. So basically convolution is, let's say, 4-to-1 mapping. So deconv is opposite. Deconv or conv transform to D, both are same. It's opposite. So it's a 1-to-4 mapping. So now you are increasing the resolution of your image. As you said, as you can see here, we started from here and we formed a 28 cross 28 final image. Doubts? For working on image or video data, which model is good? So as what is GAN? Okay, I explained about GANs, that GANs are generative adversarial network, which is game a game, let's say, in real world between police and thief. So generator's job is to create the image. Discriminator is telling that it's false or not false. So based on that, generator will be trained. So now in code, I'm showing how it is getting trained. Yeah. So which network is good? So for generative AI, in previous talk, I said that for classifiers, multiple networks we discuss, ResNet, convolution neural net, deep convolution neural networks are useful. But today for let's say in generative AI, I'm discussing different networks that are popular in generative AI domains in computer vision. Yeah, so going through the first one, which is generative adversarial network, which has a generator, which I just built here. So I as I told, in it you define your 5 layers, and in forward you will use them. So assuming you know to have knowledge of conv layer, based on that, deconv layer is a different 1 to n function. So after decon, I apply a batch norm layer. So batch normalization just to see if your covariance is not going very far. Yeah. So, and I defined 5 different layers and 5 different batch norms. And when my input will come, I will pass it through different layers. And this is how forward is defined. Similarly, this was the network, forward network, and we also need a discriminator network, which will take an image. It's just a classifier and tell us whether it's 1 or 0, real or fake. Right? Just a classifier. So it has a convolution layer. It does not have decon layer, or you can say con transform 2D layers. Both are same. So it has 5 different layers as well. And after every layer, I'm using batch norm, which is optional, but it makes your training fast. And ReLU activation functions, again, activation function, I'm not going to explain again, but they help, they help in training. Yeah. So finally, out of this, I'm applying finally sigmoid layer and sigmoid function, and finally I'm getting 0 or 1. That means real or fake. So my 2 networks are ready just by calling this class generator and discriminator. Once I have it, this is just for initializing the parameters. So my generator and discriminator this way is ready. So now, as previously have shown how to train them now. So I'm initializing some optimizers. Here I'm using Adam as an optimizer. People generally use stochastic gradient descent as a simple optimizer, but Adam works really well in GAN training. I am training it for 20 epoch. I already told you. Going through complete batch of images 20 times, creating a batch of 128 size. And so first time what I'm doing, this is an input image. This is a batch, and these are labels of the batch. And also creating some fake labels. These will be all zeros. And fake images. So basically, initially, I'm using generator to create a fake image. So I'm training first discriminator. I'm giving real image as well as fake image, and I'm telling it to tell me what are your predictions. So based on these predictions, I calculate my binary cross entropy loss. And this loss, using this loss, I'm updating my discriminator. And then based on the discriminator output, I'm changing my generator weights. Parallelly, I'm training them both. Finally, I did this for 20 epochs. And so this is the loss. Like one is generator loss and discriminator loss. As after 20 epochs, I'm comparing the loss, how loss is changing in both. Yeah, it goes 20. I should have trained it for more, but again, training takes a lot of time. Still, I'm able to get good outputs on MNIST, because MNIST is a simple data set. Yeah, but for more complex data set, you need to train it for at least 400 epochs. So how we do sampling? So this is in as any one of you have done any project or seen my previous video, know that in classifier you just give an input image again from your test data set, and you tell your classifier to tell me which class this is present in the image. Let's say cat is there or dog is there. But in generative networks, you will do something called as sampling. So you will sample from your generator. Now my generator is capable of giving me new images, new different images from what similar images what was it was trained on. So what I did, I created a random noise. I gave it to generator, and I visualized it using matplotlib. And these are the samples. These are the outputs I'm getting. So now this generator is capable of generating all different kind of samples similar to one present. As you can see, many of them are not like very different because I have not trained it well, but you get the idea of how we can generate new images with generative adversarial network. I have gone through very fast. I will be sharing this code again, but I think you get the idea how GANs are. So GANs are around 216 now. This model came in 2016, but this again has some limitations. It can generate on very simple data sets, but when it comes to very like complex data sets and generating very like different kind of images, it gets failed. It has its limitations. So firstly, if you train it on, let's say, ImageNet, which has lots and lots of classes, you will feel that it is only expert of some classes. Let's say only plain images it can generate, or car images can generate, but its data is not diverse, which is generated by GANs. Again, mode collapse, only some variations it can generate, not all variations of planes or cars. Yeah. So yeah, very high training time, and yeah, not easy to train again. Yeah, these were some limitations of GAN. Now, stable diffusion, which is a idea behind all the latest computer vision algorithms. Even if you are not getting some part of the code, just stay with here, and yeah, it will make sense for you. Yeah, so these are few websites you can try yourself, going there: DALI 2, Stable Diffusion, Midjourney, which has its Discord server. You can give it some text. Based on a text, it can generate you images, or you can give it your image and tell it what you want to change it or what output you want to do. So this is the use case of generative AI in computer vision. So all of these are based on stable diffusion algorithm, which I will cover next. Any new doubts? Okay, I don't think so. Any other doubt? Vishal, are you seeing any hand raise or any other doubt? I think I haven't answered these two. What is transposed convolution layer? So transpose convolution layer or deconv layer, as I explained, they are similar to convolution layers, but in opposite way. So let's say if you know the idea of convolution layers, they convolve over, okay, they convolve over an image and try to get features out of it, right? Using a kernel, using a kernel, but here it's a different idea. Convolution is n-to-1 mapping. You are, let's say, for cross-over patch, you are converting into one. Here, if you want to convert your small image to a high image, like large image. So here you are converting 1 pixel into 4 different pixels. So it is a 1 to n function. And from this 1 to 4 different new pixels that you are creating, you by training you will learn those weights. So eventually your network is, what it's doing is doing super resolution, increasing the resolution of your input. Applications of GANs in industry. Applications of GAN industry is similar to stable diffusion. Like you give it text, or you train it on input real celebrity faces, it will give you new celebrity faces. Fake, those doesn't exist. It will mix you, it will learn the distribution of faces and generate new faces, new dresses. Yeah, basic application is for data creation. Yeah, but new algorithms like stable diffusion has shown that you can even create videos with some text. It will generate all the video that you have described in the text. I hope this is clear. I think I have answered all of them. Okay, I will answer them. Okay, no problem. I'll answer them in the end as well. Okay, so yeah. So yes, this is good motivation about why we are learning, because they are getting very high, good results with stable diffusion. So variational autoencoder is the second model I want to cover. First is GAN, because stable diffusion model is very similar to variational autoencoder. So what actually is happening in variational autoencoder is very similar, like applications are very similar to GANs. You want to generate real data, you want them to look similar to your trained data, and want to sample all kind of different images from them. So in how autoencoders work is, you have an encoder which will encode, take all the data sets, images, and encode into a, let's say, only 10 dimension, a vector of size 10, started from an image of, let's say, 28 cross 28, and you are only get learning 10 parameters. And from 10 parameters, from that low dimension, you again want to learn the again original size back. So you might ask me, like, why I converted into a lower size and then I want to sample again from that to original size. Basically, input and output is same. So then what's the benefit of autoencoders? So in basically what you actually want to do is, if you compare it to GAN, here I have learned the distribution of these images. I'm mapping this input distribution of images or input data to a known distribution. And once I have that I have learned that distribution, I will throw away this encoder and just use the encoder. By giving it a noise as an input or some text as an input, I will get real images as an output from that. Yeah, this is the idea of autoencoders. And variational autoencoders is just because your input images can come from very diverse range of distributions, but I'm mapping it to known variational distributions. Very common is multinomial or multidimensional or simple Gaussian distribution, multinomial Gaussian distributions, which I will map it to. Can we update? Yes, we can update with text, with stable diffusion, the existing images. Yes, this is a very common applications, and we are applying in industry as well. So variational autoencoders was, it came around 2016 again. Both were very popular, GAN and variational autoencoders. As I said, encoder's job is to map all this input distribution to just a Gaussian function, let's say, or multivariable Gaussian function. Yeah, and I learn mu and sigma from that, and from that mu and sigma, now I will decode again it to the same image, but on the way I will learn this distribution. So basically I have learned which distribution these images are coming from using variational autoencoder. Yeah, very famous joke that in data science, Gaussian distribution is so helpful that, yeah, we can map probably all kind of distributions to Gaussian distribution. And also Gaussian distribution is very simple to sample from. I have shown you guys about sampling, how we sampled using GAN, and Gaussian distributions are very simple to sample from. Sample means you take some values and create new images from that values using this decoder in this case, and in case of GAN, the generator. What is style transfer? So style transfer is that in style transfer is different from generative AI in a sense that you are not generating based on some text. You are transferring your input image. Let's say you say day image to night image. Those kind of applications are using style transfer, but style transfers are, yeah, stable diffusion yeah, as I said here, stable diffusion is very important to learn these models, because they are very popular, or not just in generative AI, but like generating new images, but very popular in style transfer for resolution, like increasing the resolution, or image in painting. Let's say some part of, let's say you in iPhone, as you see, you want this person to be removed from background and you want to learn what is actually behind this image in painting is. So stable diffusion is very popular in that as well. I'll take more doubts in the end. Okay, so yeah, so we'll be covering variational autoencoders very quickly. I just want to cover the sampling part, how we can train a variational autoencoder and do sampling from it. I will be using MNIST, the same data again, set again. And now we will see how we can generate new handwritten data set that we already did using GANs. Get a feel how we can do that again with how to scroll this up. I'm not very familiar with Teams, sorry, Zoom. Okay. Is this, Vishal, can you quickly confirm, is this collab visible? Data generation with V. Okay, thank you.
It's visible. Yeah, yeah.
Yeah, so as I was saying that variational autoencoder has a encoder part and a decoder part. You can compare them to as a generator or discriminator, but analogy is different. So I am training it on real images and constructing it back again using decoder. So so when I'm able to construct all the images back, so that means that this hidden parameters I'm learning are correct. Yes, and at that time I'll stop my training, and now I will take different value of mu and sigma, and now I'm from that Gaussian distribution, I will be able to generate new kind of images. Again, I'm using torch n for writing my encoder decoder, and dot functions for my loss functions. I'm converting the hidden dimension into just 2 dimension. Like hidden parameters are only 2, mu and sigma, mean and yeah, standard deviation. Training it for here for 100 epochs, batch size of 128. I'll show what is this capacity of 2064, learning rate, and variational beta of 1. It's just a hyperparameter capacity and variational beta using GPU. Yeah, again using torch vision, which is also from PyTorch for data set, for loading data set, and for doing some data processing, I'm using torch utils. Yeah, I'm just not doing anything, just converting this to torch tensors, because in GPU training you need tensors, not numpy values. Loading again, similarly I done previously. So defining my variational autoencoder. In here, this is the encoder part. I'm naming this as encoder, calling the super function. This is how we define classes in Python. Defining first convolution layer, channel 1, output channel C. So I'm now mapping it to 64 channel. Yeah, initially you can see there was only one channel, 28 cross 28 cross 1, mapping it to 64 channels. So this capacity was 64. Yeah, so 2 conv layers followed by fully connected layers. And finally, I'm getting my mu, and log var they are using, I'm using here. So basically it's under root log of say log of variance. Basically my Gaussian distribution parameters. Yeah, in forward, I'm just using this conv layers I've created, finally getting my variance and sigma. Using these two, now I have written my decoder. So what decoder is doing that, taking this latent parameters. And here, as you can see, previously we discussed con trans 2D or deconv layers. What they are doing, from small size of image, creating a large size of image. Yeah, only using 2 deconv layers here. Yeah, so yeah, in forward, I'm just applying this, and finally I'm getting a image which is similar to my input image X. Yeah, based on this encoder and decoder, I'm writing definition of my variational encoder. In variational encoder, what I have, an encoder and a decoder. Okay, in forward, I'm applying this to what I have initialized. What I'm doing is I'm taking an encoder. Encoder will give me this, it will learn all the parameters of Gaussian of my input distribution, give me some sigma values, mu values, and based on that, my decoder will give me a reconstructed image. Very simple. Yeah. Based on loss functions, I have not explained related to variational autoencoder, but what kind of loss we should use here is that first I want my image, output image should be close to the input images. So I will use a pixel comparison. I'm comparing every pixel, how far they are. This is called reconstruction loss. Second loss, what I'm doing is KL divergence loss. So KL divergence loss is a loss which compare how far the two distributions are. Now I have learned mu and sigma, right? So using this mu and sigma, I can compare this learned distributions to the mu of sigma of original distribution. So based on these two losses, I'm training my variational autoencoder. Again, taking some more doubts. Don't we have predefined classes as we have coder and decoder and transformers in case of transformers in text processing? No, we don't have predefined classes here because we are not working in class definitions here. Yeah. We don't need any labels. We just, in case of GANs, we just need real or fake. In case of variational autoencoders, they're completely unsupervised. Yeah, so I'm initializing optimizer and training this network for 100 epochs, going through complete training data set, taking 128 each time. What I'm doing is I'm doing v.train here to initialize everything. v.train we do in PyTorch whenever we tell our network to initialize all the parameters for training. And this VE, I'm passing the complete wedge. As you can see, VE will output, what VE will output me? VE will output me these four things. One, the reconstructed image. Second, where it is, I forgot. One, the reconstructed image. Second, mu and variance. Based on these two, variance and mu, you can calculate the loss. And you also can calculate your pixel to pixel loss, because you have ground truth. Ground truth has in your input, and you can compare it to reconstructed, and you can calculate the loss. For loss, I skip this part, VE loss function. I explained this actually. It's a sum of both the losses. And then I'm just updating my weights and doing for 100 epochs. Yeah. So loss will be loss is this case, this network is trained fast as compared to GAN in my experience. Yeah, so now we have trained our both encoder and decoder. So as I promised you, decoder is now capable of giving you similar images that those were present in MNIST data set. So what I did now, it's time to do sampling. In case of your classification models, you test it, right? You test it and calculate the test accuracy. But in generative models, you will do sampling to test how well your model is performing, right? So to sample, what you do, I create a noise and I give it to decoder. So my decoder is capable of generating real images, just seeing some Gaussian parameters and just taking a simple noise. Yeah, noise, you can say a random value. Even Gaussian distribution will give you noise as in. So I'm just giving a latent vector, which is coming from a Gaussian normal distribution. And I'm getting a final reconstructed image, as you can see, because my decoder has learned this to generate images like which were given to encoder initially. How are fake and real images generated? Doesn't the discriminator discards the fake images to minimize the loss? I think it's you're asking in terms of GAN. Doesn't the discriminator discards the fake image to minimize the loss? So yeah, so when discriminator is your generator is good enough to fool the discriminator, full enough to generate full enough to is your generator is smart now. He will be able to fool him that it's a real image. So at that time, you know that your generator is smart enough now, can give you real images. Will this not? Yeah, I will be sharing all the codes. Okay, so now we have seen that various autoencoders. Based on this knowledge, I will be covering stable diffusion algorithms. So in a recap, I have shown till now with you guys that I share you guys two very important networks: generated adversarial network GAN and variational autoencoders. Yeah. So variational autoencoders are also very complex. They are very simple, but in a say that their outputs are very blurry sometimes, and yeah, so they actually suffer in generating the diversity of images when data set is very complex. In case of just MNIST, it was good. So the main reason behind that is every time we want to map our input distribution, complex image distributions to some simple distributions. So this assumption has some drawbacks. Yeah. So idea of diffusion networks or stable diffusion networks comes from there only. So idea is that there are, can we take an input image and can we learn forward diffusion is like, can we keep adding the noise to the image and finally generate a noised image? Yeah, it has two parts: forward diffusion process and reverse diffusion process. So can we learn a noised image from my input image, and can I again retrieve the original image from my noisy image? Yeah, this noise you will add, and in reverse you will try to decrease the noise or remove the noise. This is the idea of stable diffusion networks. As you can see, I'm just want to give you a quick idea of diffusion networks. I'm not going through code or anything because these networks are complex, but I will give you enough. Yeah. Uh, Vishal, everything, am I audible? Everything good?
Yes,
Hello?
everything is good. Fine.
Okay. Okay. So in forward, you will keep adding noise, and in reverse, you will try to remove this noise. And as you can see, forward process is very simple. You will take a noise, just keep adding, keep adding some noise after T steps. T is generally taken as to be 1000. And in reverse, you will try to denoise this. And for this denoising is not a simple process or tractable process. So we will learn some neural networks to denoise it. Yeah. Reverse process learns the conditional probability densities using neural networks. Yes. So yeah. Okay. So this small changes in every network, every image, every step is sort of this in probabilistic distribution models. In terms of the distribution models, we call them Markov chains. So what Markov chain is? In Markov chain, what is the definition of Markov chain is that your xth steps, probability of your xth step just depend upon xt minus 1. Here q of xt given xt minus 1, your this output depend upon your only just previous output, not anything else in the world, because you will take this image, just add few noise, and this will become this image. At every step I am adding same amount of noise here. That's how it will become a Markov chain. Yeah. So if you want to calculate this complete, you will just iterate over T steps and you will find your complete density function. And yeah, so you know what noise you're adding. So you just knew mu and sigma to calculate this, right? At every image, you need your previous image and you need some mu and sigma, and you can calculate the image. I think this is straightforward. What is not straightforward is reverse process. So yeah, so diffusion models are very latest. So first diffusion model, this idea just I explained, forward and reverse process, came from this paper. I will be sharing the slides. You can cover this paper if you are interested in this domain. These three, only these three papers you need to understand to get a complete idea of stable diffusion algorithm. First is denoising diffusion probabilistic models came in 2020, which explained this process of forward and reverse and how a UNet, which is a very popular neural network, can be used to reverse this process. So you will again ask me that we are in the end we are only calculating the input image. So what's the benefit? So the benefit is now this neural network will be trained to sample from noise as well, or a text as well. So we'll give a text and a noise and it will give you the image you want. This is the application. Similar to GAN, variational autoencoder, and now in diffusion models. So as I was explaining, this idea came from DDPM paper, denoising diffusion probabilistic models. Yeah. So later in 2021, this was improved by DDIM paper, because as I will discuss with you, the sampling, these models are there for many years, but they takes a lot of time to train. They are not very easy to train as GANs and variational encoder. This paper made it simple, made it practical. This boom came because of DDIM paper in 2021. Yeah, and finally the LDM, latent diffusion model paper. Latent diffusion model has another name, which is called a stable diffusion. And this is that paper which use it. Actually, these two papers, you were sampling again from a noise, but this paper showed how you can use a text, and based on that text, you can create an actual image as you want. Yeah, I hope you can now visualize why this domain is so popular, why DALI 2, which is a website or a model from OpenAI, why it is so popular, just based on these three papers. Yeah. So in paper, they have shown that, let's say, if you want to create the noisy image at Th step, you don't need to iterate it. You have your noise, you have standard variation of noise, you have previous image, you can get the next image with this closed form. Just very simple. If you want, if you give me my image as an input and you tell me after T steps, how much noise will you calculate? So based on that, I don't need to do T steps. So this closed form will give me Tth step image, noisy image. Forward step is very simple because you know what noise you are adding. What is difficult is reverse process. Reverse process is not so simple because removing noise is not so simple. So for that, we will train our neural networks and we will learn a distribution P of theta. So given more noisy image can be repeat this process T times and get my actual image back from noisy image. So this network will learn all that theta parameters that will take a input less noisy image T at T step and give me T minus 1. So these are the parameters we will learn using this neural network. Yeah. So in training, I'm not explaining the architecture of UNet. I'm just giving you an idea of how these networks work. I will randomly select a time frame, converting it to time step embedding, giving it a noisy image. How I will calculate noisy image, I will take an input image and add a Gaussian noise. And that Gaussian noise, how much I will add depend upon this time steps. Yeah, and my training of UNet, how I will train that reverse process is that I will try to predict what noise was added and I will compare it to the original noise. And if they are very close, I'm making them, I'm training it to close to my original noise that I have added. Yeah, again, the same thing. This is the noise which my UNet will once I have noise, I can just subtract it and get the original image. So this objective function is very simple. I am just learning to predict that noise and I have my original noise. How far they are. My aim is to minimize this. Yeah. So this was the idea of first 2020 DDPM paper that I mentioned earlier, but still DDPM network, this network is very slow. As you can see, I have to repeat this process. Going quickly back. the original slide. I have to repeat these steps 1,000 times. This makes it intractable, very, very slow. So to just sample this much images is 20 hours, just in sampling. I'm not talking about training part. GANs are very fast in compared to, yeah. So that's how the second paper, DDIM paper, which showed that you don't need to repeat this, do this for 1,000 times. They trained their network in such a way that now I can predict T of 3 just based on T of 1. I learned all these thetas so that now I don't have to repeat the 1,000 times. I can take, let's say, 7 based on the 700 step. Can I learn 473 step? Yeah, in this case, can I predict the third less noisy image based on the first part? Yeah. So this was the adaptation that's shown by this paper. So now how come sampling became fast? Earlier they have shown that using the 1,000 and using some 20 T steps, we can get the similar outputs using their method of training. Yeah, this is as I can say, now you don't have to sample for 1,000 steps. You will take some T and you will repeat the sampling process for T times. Yeah. So again, now stable diffusion paper, they shown how we can use text, and yeah, we can. Earlier we were just generating new images just based on a noise, like LDA paper or stable diffusion paper also showed us how we can incorporate text and generate output images based on some text using these diffusion models. And they made it super fast because they first converted their images to slow, short, latent space of smaller size. That made it super fast, almost as fast as GANs. Can take some doubts now. I'm almost in the end of the slides. Why stable named added to here with diffusion? Yeah. So actually, I showed you 3 papers. Yeah, why stable is as it? That's a good question. Like, I am quickly going back where papers. Yeah. So stable diffusion is another name of latent diffusion network. So when they become very popular, OpenAI only named it as stable diffusion because this type of diffusions are very fast. They're very stable. They will converge always. Always they will give you the correct outputs. Yeah, because of this DDIM paper hack. Just a name. Actually, originally it was called as LDM, latent diffusion models. Yeah, I think I showed you how you will train it, how I will provide these slides, go through. This is, I'm not expecting you to know everything about diffusion models, but just an idea how the forward step works, how the reverse step works, and what are the key papers, which key ideas, where these ideas came from. Okay, so I think I have answered this. Why do the first noise and then denoise diffusion? Yes, the idea is similar to variational autoencoders. Like if you can remove, if you from a noisy image, if you can learn, you can make new images. You can get your original image back. That means from a well-known noise, you can also predict real looking images. So that's the idea. So basically in machine learning or computer vision, when you add noise, you will make your network more robust. You will generate. It's good for more noise you will add, more difficult your will be for your network to do. So it will generalize more. But here idea of noise is to generate from when I say noise, basically sample image comes from Gaussian distribution, which is just a noise, does not carry anything. Yeah, I think I have answered everything. Okay. Yeah, will be also what validation metrics. Validation, as I said, validation will in generative networks will come from human eyes. You cannot validate images as such, because yeah, it will come from your human eyes. Yeah, how good the output looks to the training network, or is it? So yeah, the next future is Gen 2, which is already released, which can create a text to video, like it will generate a movie based on your script. Pix to Pix network, you will give it a input image, tell it to change. This is application of stable diffusion algorithm. Yeah, I'm concluding it here. Any hand raise or any doubt you can ask me. We went through generative AI applications in computer vision domain, covered some code with PyTorch, went through it very fast, but I had it like I could do this only. 3 videos where these 3 papers were introduced, basically the conferences of these 3 papers. I think I should wrap up. I have, yeah. Yeah, want adding the noise leads to overfitting. No, removing noise will generalize it. It will, uh, it will, overfitting happens when you have less data. You aren't able to get your actual image back. Then that's overfitting. Noise will make it more generic, especially to generative networks. Yeah, just if you are interested in generative AI, you should cover these 3 ideas. I have given you a right direction, I think, if you want to, if you're interested in this domain. Thank you, Vishal. I think if you can guide me if I have missed any hand raise or any doubts, I
No,
think
no.
I have
Yeah,
covered it. Yeah.
yeah.
So, yeah. So if you guys have any doubt, you can still ask me. I'm here. So this is pretty much from my side, Vishal.
Okay, okay, Abhishek.
I don't expect you guys to know everything because these ideas are very complex, but I've given you an idea like how these latest algorithms are working. Yeah, thank you.